Hello and welcome to our day 2 of the digital event about extending OPC UA to the field level. My name is Peter Lutz and I'm the responsible director for field level communications in the OPC Foundation. Before I go quickly through the agenda so you can see what you can expect from today's sessions, I want to quickly go through the most important organizational topics, mainly for those that missed day 1. So finally everyone is then aware of how the webinar is working. Now first of all the attendees are muted completely during the webinar. This is in order to take out any potential background noise and to allow everyone to fully concentrate on the content and the explanations. Also, the panelists are muted, usually muted, except when they give a presentation and activate their audio and optionally their video. Also for the Q&A session, the panelists will activate their audio and optionally video to go through the questions that we collect during the webinar. Collecting questions, this is the next important topic. You can use the Q&A feature of GoToWebinar to submit questions to the speakers. They will either directly been answered in written during the webinar, if possible. Otherwise, they will be answered and explained during the Q&A session. And for those questions that we are not able to answer, maybe because they come in late, or maybe because one of the panelists is missing during the Q&A, we will then deliver the answers after the webinar. This brings me to the next important topic. You as attendees will receive after our event, just give us a few days for that, compilations of all the slide decks, also links to all the recordings, and the compilation of all the Q&A, so you can then share it with colleagues or have again a look at the different content. So you will receive a mail from us a few days after the event. I believe that's now all, maybe except the chat function. In case you have any technical difficulties, use the chat function of GoToWebinar so we can reply to you and hopefully help you in case of any difficulties. With that, I think we can now have a look at the agenda. Now, for those of you that missed the day 1, you see here an overview of what we actually presented yesterday. So we had the keynote speech about overall vision of OPC Foundation. We gave an introduction into the various aspects about extending OPC UA to the field. We had a presentation about use cases for controller to controller, and then had 2 technical presentations about some of the core concepts for UAFX, information models, and connecting devices. And we concluded the day with a live demonstration of a multi-vendor demo and the Q&A session. Again, if you missed day 1, there will be recordings available and the slide decks. Now, what is the plan for today, which is day 2? We continue with technical presentations. We start in the first session with concepts for offline engineering and explain how security in combination with UAFX is working. We then have a second session which is focusing on networking aspects. So we will have first an introduction into networking in general, but also including TSN. And we then have a dedicated presentation about 5G integration into the OPC UA framework, including UAFX. Finally, we have one demonstration about UAFX over TSN, and we will also have an additional one not listed here, which is a demo on running OPC UA and UAFX over 5G. Also for day 2, we then have the 1 hour, maybe a little shorter depending on what kind of questions we have, the Q&A session. Now, what is the plan for day 3? This is the day of tomorrow. We will have, first of all, a dedicated session on OPC UA safety with an introduction and with explanations to 2 important development projects. One is about the safety stack. The other one is about the safety test tool. We then have a presentation about UAFX profiles. This is very interesting because it talks about how to combine the different elements in order to create a concrete controller implementation. So I think this is very interesting to hear. And after that, we will also have an explanation how this controller profile can then be combined with existing or future companion specifications. We will present the plans for certification and conformance, and then have a look on the next steps and what is the content of the next project phase. Okay, so now I think we can get started, and I like to introduce the first session of today. For this, I will give first of all a quick overview what aspects we are now looking at in the following. So you remember for sure the slide I explained on day 1 with the introduction, which is about the communication stack architecture for OPC UA and the UAFX extensions. So yesterday we got technical insights on the concepts of information models and connecting devices for so-called automation components. Today we are looking into the concepts for offline engineering. So this will be the first presentation we have in this first session, and after that I think what is also extremely interesting is then an explanation about how we are using and adopting security for UAFX controllers. And this is then the second presentation in our first session. With that, I'd like now to hand over to Emanuel Kolb first for presenting to us UAFX offline engineering, and after that we have Jack Visoky and David Smith talking about UAFX and the security related aspects. Emanuel, the stage is yours.
Hello, my name is Emanuel Kolb, and I would like to introduce you to the UAFX offline engineering concept. So here is a short outline of my talk. First of all, I want to show a slide on the lifecycle phases in industrial engineering. Next, I'm going into some details on engineering information exchange, and then I will introduce a central concept of UAFX offline engineering that is called the descriptor. Next, I'm explaining a little bit about the automation ML modeling language that is used in the descriptor. Then I will show a modeling example, and I will lose some words on implementation and tools. Finally, let's have a look at UAFX offline engineering conformance units and profiles. Looking at the industrial engineering lifecycle phases, one first observed the workflow steps that are happening in every plant, from planning, design, simulation, commissioning, operations, maintenance, and finally decommissioning. On the other hand, there are also different levels of integration to be done. You start with a controller or a device and integrate things to a higher level like machines and skids, and finally things get delivered to the plant and there everything gets assembled together. This has of course to do with different companies and stakeholders that work on these different levels. And what you can see also, there are two tracks where things are connected. The most important one is, of course, the value chain, where the things gets delivered and integrated. But this value chain is also predecessed by another chain, which is, I would call offline engineering. In this chain, data is exchanged between the different stakeholders in order to integrate things already before the hardware is assembled on site. And this is the focus of the talk here. So what kind of information is exchanged between component vendors, machine skid builders, and system integrators? First, of course, there is information on the hardware, on the assets, on the capabilities and constraints of the hardware of a controller or a device. Then, of course, there can be things like documentation and drawings, user manuals, installation instructions, additional notes that a system integrator has to observe if he wants to set up these devices in a bigger system. One additional thing machine skid builders will provide in their work is, of course, programming. Controllers need to be programmed in order to execute the right functions. These things are then in the information model represented as functional entities. On the other hand, communication between machines is quite important. So communication also needs to be designed, and this is represented here by the data set icon here on the right side. So machine skid builders will exchange information on data sets, I/O variables, in order that the communication can be set up in the right way. Finally, sending this information to the system integrator also includes connection configuration and asset configuration. Think of a modular asset where a controller can have various I/O modules included. So these kind of things also will be provided to the system integrator. The connection information is quite important for starting up the system in order that the connections between the devices and the machines are set up in the right way. So what is the right format to exchange all these information between the stakeholders in an engineering project? And here exactly comes a new concept that UAFX is introducing in part 83 of the specification. It is called the descriptor. So what is a descriptor? A descriptor is basically a vehicle to transport information from one stakeholder to the other. The information it contains can be, of course, of various types, and this you see here on the enlarged box on the right side. The most important kind of information is, of course, an information model, like the OPC UA has defined for industrial devices. Next, there can be also attachments, binary information. This could be drawings, documents, or pictures, or even software components. Another feature the descriptor has that it can embed other descriptors. So if you want to put more than one descriptor together, for example, for producing a product family descriptor, or you have assembled a remote I/O module with various modules together, then you can use this feature for having a kind of super descriptor. Next, a descriptor can also have references to external content. So it can either reference resources on the internet or on your local hard drive. And finally, a descriptor can also have digital signatures. This protects the integrity of the information. So what is a technology that is used for making a descriptor? From the outside, a descriptor looks like a file, but it's not a single file. It's basically a document container like you have, for example, in zip files. The special technology here is called AML container, and the suffix for the file is .amlx. If you look now further inside of this document container, the information modeling files are automation.ml files. And if you look at the signature, there is a standard for defining digital signatures, and this is the XML digital signature standard. We will have a further look at automation.ml in the next slide. In this slide, I want to say a few words on the automation.ml standard, short AML. AML is a neutral data format based on XML for the storage and exchange of plant engineering information. It's an IEC standard, IEC 62714, and it supports the well-known object-oriented modeling concepts. The information is stored in files with the extension .aml. For the integration of more than one AML file, another concept is defined that is called AML container, AMLX. This is a document container for bundling of files together. This can be AML files, but this can be also non-AML files. It has a file extension .amlx, and it is based on the Open Packaging Convention standard ECMA 376 that is, for example, also used for the Office documents from Microsoft. And it supports digital signatures based on the XML digital signature specification. So why automation.ml was chosen as the modeling language for the descriptor? First of all, it is an accepted and established modeling language for industrial engineering. It has modeling concepts similar to OPC UA that enables to represent OPC UA information in AML. It is quite open for incorporation of other modeling standards, for example, Collada 3D data or PLC open information can be integrated quite easily in AML. Next, it defines a document container format, so multiple files can be put together. And digital signatures are also defined for handling integrity of information. Finally, Automation ML was adopted by OPA's MTP in Industrial 4.0 for modeling of engineering information. So this slide shows you an example of the OPC UA, of an OPC UAFX information model modeled in Automation ML. So you barely see any difference to an OPC UA structure. On the left side, you see the initial structure of the root folder, the objects, the FX root, and an automation component. You also see the assets folder and further dive down into some assets of a modular component. It looks like familiar to once you know an OPC UA structure. On the right side, you also see some libraries. These represent a little bit the object type and variable type section of OPC UA. So you see some libraries here that are provided by the UAFX standard together with a specification for a jump up start with the Automation ML modeling. On this slide, I want to give you a quick overview on implementation and tools for handling descriptors. A basic set of UAFX AML libraries is provided as part of this specification. There is a tool that converts a node set to an UAFX AML library currently being developed by OPC Foundation. AML Engine SDK is a .NET framework provided by automationml.org that can be used for integration of AML into engineering tools, like implementing a descriptor import or export. A general purpose viewer and editor for AML is available at automationml.org. You have seen a screenshot of this in the previous slide. Finally, a prototype for digital signing of descriptors was being developed as part of the prototyping activities in FLC. Thank you.
Hello, welcome. My name is David Smith, and I am accompanied by Jack Visoky. And we'd like to give you a brief overview of the OPC UA field exchange security mechanisms that are included in the C2C release. Next slide. Jack, thank you. First of all, I'd like to say that the OPC UA protocol has a lot of great security features that are designed in by the foundation. So it makes absolute sense to reuse as many of them as possible. First and foremost, secure conversation is required for all products to use. And underpinning that is identity based on digital certificates. Because we know that OPC UA UAFX is going to be largely application to application, we made sure that we took that into account by requiring products to support the digital signature token when logging into an application. We also know that many embedded devices are going to be using UAFX. So we're requiring that all products also support elliptic curve cryptography because the keys are smaller and more amenable to embedded devices. Lastly, we also know that in the industrial world, motion and high performance applications may not be sensitive to having information disclosed, but they absolutely need to make sure it has not been tampered with. So for this reason, we have sign-only mode as the minimum default security. Encryption is required for products to support, but it's optional when it's to be deployed. So it's up to the customer at that point to decide whether or not they want encryption for their messages. Lastly, we also made sure that the pub/sub security is secured. And we're doing that by using the push model. Jack will get to that in a little bit in the future. But that is really reusing the client server connection to distribute keys. So on the right, you can see that we are making sure that we reuse the layered transport security to ensure that there's a robust security for UAFX. Next slide, Jack. So I'd like to walk through a little bit of the connection workflow. This is a simplified version, so there are some missing steps, but the gist of it is there. At the beginning, at the top in the center, we have the connection manager. And the connection manager has to interact with a portion or a component called the security key service. This is the key service that distributes keys to pub/sub participants. In OPC UA, UAFX, this security key service will be required to be part of a controller, but it may also be standalone. So for that reason, it's drawn as a standalone functionality right now. One of the first things that the connection manager does when it knows it has to create a pub/sub connection is it will ask the security key service to create a security group. It'll configure that security group with information about the connection, how long the keys have to live, also some information about the devices, the IP address that they have, the security mode, etc. After that, the connection manager does its usual workflow to establish a connection. So it'll contact the device A and device B as well. It'll configure pub/sub connections. It'll tell it to start. If the security key service is part of the connection manager, then the security key service will then be triggered to push the security keys to device A or device B. If the security key service is standalone, then the connection manager will have to make an additional call to the standalone security key service to trigger the push mode for connection. After that, the pub/sub connections should be fully set up, in which case device A can push or publish messages to device B, which is the subscriber, and the message security is intact. At some point, the keys will have to be renewed sometime in the future. The connection manager will have told the security key service when the keys will expire, and then the security key service will automatically renew for the new keys and then automatically push the keys to the participant. This is to ensure that there needs to be no human interaction to make sure that the connection is still up and running. So I'd like to introduce Jack Visoky. He's going to cover the next 3 slides, and he's going to talk a little bit about what we've also had to add to the UAFX specification to satisfy some of its functionality.
Okay, thank you, David. So first thing to talk about here is around role-based access control. So of course, it's important to protect the transport and the data, but this idea of access control is also really important, and of course something that OPC Foundation has already recognized and put a lot of work into the specification. So again, we wanted to reuse much of what was already there, and we did that. But there was an area where we wanted to add something. David talked about the connection manager as something that's able to to create connections for OPC UAFX, and we wanted to have a special role around that. So we added a special role called the connection admin that was added in part 21, and that is essentially the role that is tied to the connection manager. So that's establishing connections, starting and stopping connections, things like that. So that's a new role. But largely, other than that, we just reused the existing roles. In the future, it's possible we've discussed adding some other roles, maybe. Although for now, for this controller to controller release, this is what we felt was minimum and what was needed for a robust release. Okay, so moving on to pub/sub security. David already mentioned this a little bit and kind of walked through some of the flow. But the pub/sub, it's really the bread and butter of OPC UAFX. That is the data exchange. So this is of course important to make sure we get all the pieces right and have the appropriate security protections here. So first thing to mention is, we want to protect the data. And as David had mentioned, you don't have to encrypt the data. There's often going to be use cases in this industrial space where encrypting the data doesn't make sense, and you're just essentially wasting processing power doing that. So you don't have to do that. It's optional. But the sign only or sign and encrypt, you at least get the protection against somebody from somebody tampering with the data. So you protect against that, and if you want to, you can optionally add the confidentiality on top of it. So at least we have the minimum sign-only protection. We have also had a lot of discussions about some future support for DTLS. This would be another mechanism for protecting the pub-sub communication beyond the existing one. This would be an optional mechanism. It wouldn't be required, but for some use cases, we felt this would make sense. So you could always use the existing pub-sub security, but optionally DTLS would be another option to be used. Right now, we're working through the definition of this and working on prototyping. So I will ask if anyone is interested that might be listening to this and participating in the prototyping effort for DTLS support. Please do contact somebody at OPC Foundation. You can certainly talk to myself or David or anybody else who's really involved in the security working group or whatnot. Beyond that, we focused heavily on the push model for key distribution for protecting pub/sub. And again, this is back to the existing pub/sub security, not the DTLS. In this case, keys need to be distributed to the publishers and subscribers, and the push model, although the pull model is optional and it can be supported, the push model was the one we made required, and we defined that within the specification and added a little bit to part 14 in support of that. And one other thing to mention here is around SKS support. So one of the use cases that we felt would be popular would be for one of the controllers to serve as the SKS. So essentially, you have an SKS embedded within the controller. You could, of course, have an external SKS, maybe a software server or something like that. But for many of these use cases, having it embedded in the controller is likely going to be a pretty good way to go. So we did define some requirements around that, around the profiling and things like that, to allow for the controller to serve as an SKS. All right, the last thing to discuss here is around the offline descriptor. So I'm sure today we've talked about the offline descriptor in other areas, but this is something that also needs to have some kind of protections around it. So the first thing to mention is that this is based on a standard, the Open Packaging Convention. So there's already some digital signature work done for that. So we were able to reuse that. So that made a lot of sense. We've also allowed for multiple parties to edit the descriptor, but still maintain the authenticity. So that's the extensibility aspect of the Open Packaging Convention and the way the digital signature is applied. And then the last point to make here is that we wanted to try to align the signatures on the offline descriptor with the existing signature mechanisms as much as possible. So we're talking about here, the signatures on certificates. We already have a lot defined for what's required and how that's done with certificates using RSA keys or ECC keys and various curves, things like that. So we essentially just reused many of those things so that the signature on the descriptor would be consistent with the ones on certificates. Okay, that is all we have for today. So I thank you for your attention. Appreciate the time today, and I hope that we see some more participation in this effort. So we welcome any additional participation from any of you who might be listening today. So thank you very much, and have a great day.
Thank you all for your presentations and for sharing with us insights on offline engineering and security. In the following, we would now like to concentrate on network-related aspects. And for this, I would like to quickly introduce to you the approach of the OPC Foundation to deal with different underlying transports. You already have seen this slide in my introductional presentation. This is about the various use cases we have with OPC UA today and with UAFX in the future. And if you look at the different numbers, it's obvious that we deal with many different types of communication. We have wired communication, we have wireless communication, we have a communication that requires a high bandwidth. We have requirements that have quite strict requirements on latency and jitter, especially when we go into the field level itself. So we somehow can summarize that the various applications and use cases have different requirements on the so-called quality of service. Now, I would like to again use the communication stack architecture graphic to first of all give you a more abstract understanding on the approach OPC Foundation is taking. You have heard many times or multiple times already that the OPC UA framework is transport agnostic. So whatever you find here in the red box is not depending on what kind of transport protocol or physical layer is finally being used. So we have client server and pub/sub, and that can be transmitted over different underlying mappings. I already explained to you that we have applications with quite diverse QoS requirements. Now the challenge is to map these application-specific requirements to the underlying network, which provides a certain quality of service to the applications that make use of the networks. And for this we are mapping the QoS requirements to the underlying network. And this is now the overview on what you now hear more in detail from our technical experts that talk about the different mappings, that talk about quality of service, and especially then concentrate on Ethernet TSN as well as 5G. One important slide I just want to quickly repeat, even I know that Lukas has included this as well, but I just want to ensure you understand the importance of the IEC IEEE 6802. This is about sharing a common network infrastructure among different IT and OT protocols. And we are strongly committed to this 6802 TSN profile for industrial automation. Second, I want to mention the Memorandum of Understanding and in the meantime the liaison agreement that we have signed with the 5G ACIA. And this is about OPC UA integration with 5G. And this is then the second presentation we hear from Alexander, giving us insights about how this fits together and how we can ensure a smooth integration. And with that, I'd now like to hand over first to Lukas Wuesteney, talking about UAFX networking, and then after that we have Alexander Ziegler talking about OPC UA and UAFX with 5G. Lukas, the stage is yours.
So, yeah, thank you, Peter, for the introduction, and welcome to the session about the networking topics of UAFX. In this session, we'll focus on the Ethernet networks and the integration with TSN and deterministic networking. So, let's start. You have seen the slide just before into this introduction. And as you mentioned, there are different types of application with different requirements. And now the focus is that we need a stable and reliable network to serve all these critical applications. In UAFX, we focus on this specific area where we have different types of applications with different characteristics in their communication, and these characteristics need to be taken by the network and handled. For reliable networks, the determinism is a key metric, and the IEC IEEE 6802 is an industrial profile that is currently still in standardization, and industrial automation vendors seem to drive into this direction and focus on building their networks based on this profile in most scenarios. It's not the rule for everything. But we didn't want to reinvent the wheel, and therefore the UAFX aligns with the 6802. This is a little bit challenging because it's not finished yet, and we basically needed a solution. Therefore, we propose a few things that I will introduce in the following, but they are compatible with the 6802. That was always the goal. If we look again at the stack that you have already seen also a few slides before in Peter's introduction, you can see that there are a lot of elements that are important for an OPC UA-FX communication. And I now want to highlight two elements that are important for the deterministic communication that we focus on in the following. The first is already marked in red. This is these are parts that are introduced by the OPC UA base group. So within the UA-TSN working group and the base network model working group, we defined a few elements that the device uses to present, on the one hand, the application requirements, but also on the other hand, the capabilities presented by the end device. These elements are necessary to have a common way of presenting the requirements and capabilities across different networking devices, not only UAFX, but to be compatible in general. And on the second hand, we have the requirements and capabilities that the networking, the lower layer, where the communication is basically going on the wire, on the media, all these requirements, capabilities. They need to be aligned. So on the one hand, the application should not request quality of service that the underlying network cannot deliver. And the underlying network basically should be focused on what applications really need. As I introduced 2 slides before, we have specific types of applications in our UAFX networks, and that's always what we had in mind. We aligned the requirements that we want to present to the network as application requirements, and we also had in mind what the network needs to serve. Within this presentation, we now focus on Ethernet TSN. Later, you're going to hear a little bit about the 5G topic. And as Peter mentioned, everything that we have in the upper half of this diagram is independent of the lower 2 bars, which is the physical medium. So everything for the upper half that we present in the information model, that is exactly the same later also for the 5G presentation. As you know, the OPC UA-FX release is upcoming, currently in member review. It consists out of 5 major documents. For this presentation, the most important one is the networking part, the part 82. That defines basically the workflow of configuring and integrating the networking with the application. We designed an integrated process or integrated workflow such that the application engineering and network configuration is aligned together and they are not separate things which are not compatible to each other. In the first release, we focus on the controller-to-controller, which is a little limited, and we are also basically still working on the next steps. I'm also having a short outlook presentation at the end. And the next release is controller-to-device, device-to-device, basically will take on from where we are now. And yeah, so but we basically provide the foundation for that. Two other parts that I will touch slightly in my presentation is part 81 and part 84, but you'll see that later. If we look now at the deterministic communication with TSN on OPC UAFX in the C2C release, we basically have three types of devices. UAFX is focused on end devices, but still the bridges are there as well, and we also have bridged end devices. Therefore, we basically have these three elements that are represented in certain forms in there. In general, we focus on the communication between the controllers. That's always our main goal. We have UAFX controllers, and they communicate with each other either via client server or via PubSub. For the C2C release, the communication, the cyclic communication is PubSub. Client server is currently used for the configuration, but things will advance in the future. For the controllers, we have a UA information model that basically specifies the PubSub priority, so the priority of our cyclic communication, of our control communication. And we have specified that we need VLAN tagging for the layer 2 communication. I will go into detail later what that means. For the bridges, we specified, and that is aligned with the 6802, a few key components. Not all of them are mandatory, but in general, a few key components. It's the VLAN bridge, so we need VLAN support to distinguish different types of traffic within the network, to distinguish the priorities of the VLAN tags. There are a few mechanisms to enhance the communication of time-critical applications. Therefore, we have frame preemption and scheduled traffic. And as I already mentioned, we need robust and reliable networks. Therefore, we have filtering and policing mechanisms included. And also the path control is there for a stable communication in the network. The configuration of the network elements is defined, or is going into the direction of netconf, because that's basically where the networking world, the bridge world is heading towards. Not everything is possible there yet, but that's basically the foundation or the direction to go. And for the end devices, it's the client server. As I already mentioned, we now have these requirements for the controllers, for the end stations, and a few bridge requirements, and not everything is mandatory. And the question is now, which elements do I need to start general UAFX and to have an integrated networking and application workflow, and which elements can I additionally use to get better performance, to get more reliable communication. So in part 84, we have the definition of the facets, or basically the requirements to the devices. And the mandatory element is that a UAFX station, so basically a device, you can say, needs to support the information model of the base network model. That means needs to present the network capabilities that it has, so which interfaces, for example, it has. Additionally, it needs to support LLDP topology discovery, such that basically from the outside we can observe which devices are where. And it needs to support the VLAN tagging. Then the optional thing, as we are focusing on the end stations, and not every end station has a bridge and all these topics. We have specified 3 different layers, basically, of how you can advance your network. The basic one you can support is VLAN and remote management. Remote management is the netconf topic. Then, if you want to advance it a little bit, then you have time synchronization and frame preemption on your bridge component in the network. And the full element would be the time-aware shaper and others. So this is just a small subset of what is behind these different facets, but just that you get an indication, basically, how this builds up on each other. So yeah, let's start with the workflow of how we integrated the UAFX networking into the application engineering process. First, we have on our first controller the specification, or in the engineering tool of the first controller, the specification of our project, of our program. And based on the selected devices, there is supported QS. That's a list of basically what type of network capabilities the device will have. Right. This is then exported in a descriptor, as you have just heard in the offline descriptor presentation, the format to export it to a different controller engineering tool, so that basically 2 different engineering tools can work on the same project. Then the second engineer basically imports the first selected QS, also specifies the remaining of the program and basically what needs to be programmed on controller B, and selects the final QS. That needs to be a subset of basically what both sides of the communication support. And we have the final OPC UAFX connection with a selected quality of service. This is then programmed onto the controllers, and on one of the controllers, or as a logical entity somewhere in the network, you have the connection manager that basically then builds up the connections with the selected quality of service. Until now, we just focused on the controller, so there was no networking step for now. The next step is the network configuration. In the C2C release, this is still a little decoupled, but fits perfectly in the workflow. So the network administrator provisions the network. This means rolls out a complete configuration, such as VLANs, maybe time synchronization, or additional TSN mechanisms. And in general, establishes the connectivity between all the controllers that need to communicate. If we talk about TSN configuration or network with deterministic capabilities, there could be 2 examples. There are many more, but just 2. This would be a static configuration that will not be changed too much during runtime. Either, for example, a QBV configuration where just 2 different or a few different priorities are distinguished in static gate entries, or we assign the frame preemption mechanism to some priorities as expressed and some others as preemptible. This is for now a relatively static and decoupled process. Later on, I will show you basically how we are working on integrating that with a more dynamic and more automated configuration mechanism. So now we have our applications on the controllers. We have a fixed requirement on the quality of service, and we have a static network configuration. As you can imagine, not everything that was programmed somewhere offline for controllers now fits perfectly to the network. This can just be different use of VLANs or IP addresses or some other topics that just nobody was aware of before. So we need an optional step to integrate now these two things together. Therefore, the system integrator with a generic OPC UA client or with vendor-specific means basically is doing a few or can do a few integration steps. One of them would be to modify the network interfaces. So for example, if before the default VLAN interface was the VLAN ID 100, now maybe it's 200 based on what the network administrator already has as other components in the network, then this needs to be upgraded or updated in all the controllers. The second thing is the priority mapping table. The priority mapping table, and I will have that on the next slide in more detail how it basically works. But the mapping table translates the application quality of service requirements to actual priorities in the network, such that the application, independent of what the network has configured as quality of service mechanisms, can get actual quality of service guarantees. This also needs to be updated to how the priorities in the network were selected. There's also a default table in our specification. So in general, for normal applications or normal deployments, this can work out of the box. But for more complex deployments with also other protocols in place, maybe a few adjustments are needed. And therefore, we have exactly this step now. And as a last step, and that's the general approach of UAFX, before the connection is rolled out by the connection manager, still basically all parameters of this connection can be adopted. Let it be the quality of service requirements, but also any other parameters of the connection, like, for example, the cycle time, the interval, or something like that. So now, in the final step, we have the connection establishment, the operational phase. And I'll highlight the different steps step by step now, as this is the figure of the draft and is explained in the text. First, the connection manager sets up the connections by triggering the automation components on each of the controllers and handing over the finally configured UAFX connection. These are then translated for now in pub/sub connections. So basically, these automation components, function entities, they trigger now the creation of the actual pub/sub connection in the devices, such that the communication can start. I have already talked about the supported and selected quality of service, but haven't specified exactly what that means. In this first release, we focus on the priority based. So that's the decoupled mechanism. The end device with a priority just specifies this is more important than the other thing. In the next steps, there will be more differentiated quality of service categories. But for now, we have the quality of service category priority. And for the C2C unsynchronized communication, we have specified this priority label green to specify a differentiation between different types of traffic later on. So for example, there will be other labels then for the communication that is synchronized and has timing requirements, for example. And now what you can see is that this mapping table that we have here also fits to what the selected quality of service basically specifies. And once we now have our communication from our program in the UAFX application through the pub/sub stack onto our network, the packets pass this priority mapping table, which is defined in the part 22, the base network model. And there is the translation of the mapping URI and priority label, so priority and green, as we have in our pub/sub application, to actual priority values on the network. I've now talked a lot about VLAN and PCP because TSN mostly is associated with layer 2 communication, therefore uses VLANs and PCPs as priority values. But this priority mapping also works for layer 3 communication. So also this table specifies a DSCP value. And if you have IP communication, then these layer 3 priorities will be inserted into the according fields in the header. As a next step, then the frame goes onto the wire, and you can see now the pub sub traffic down here matches the PCP4, so basically goes onto the wire and gets the quality of service that's configured for PCP4. And the important thing is that this mapping table in the default state is fixed in our specification. So basically, the application engineer, or the network administrator that configured these quality of service mechanisms before can already guess that all this type of traffic for the controller to controller communication will either use PCP4 or DSCP of 46, and therefore can set up the network to handle these priorities accordingly. And in future, new types of traffic for all the different applications, as we've seen in the introduction, motion or IO traffic, they will have also dedicated priority labels and default priorities, such that the network administrator or the network configuration can use these and set up the network already accordingly for that. And at the end, once the controllers start communicating, everything is integrated into each other and basically fits together. So as we have seen now, these steps are tightly coupled. So the application engineering, the network configuration fit together, as we also have specified these transitions between both processes with default values. So based on the default values, the whole workflow is basically seamless integrated. But still, if there are changes due to other protocols that require changes because they already, let's say, occupied certain values for their traffic, then the system integration needs manual adoption at the end. And in future, we want a more plug-and-produce approach for the whole networking. And here it's not TSN, but this counts in general for the networking. And the goal is that the network configuration automatically retrieves the requirements and configurations of the end devices and can adopt the network configuration independently. And these few steps I will present now here as a summary. First, and that's going to be the same as it is now, the application engineering process specifies the application quality of service requirements. That is always the foundation for all of our work that we are doing, because at the end, the network needs to serve the critical applications. Second, these applications are deployed on certain devices that have requirements, that have different capabilities of TSN mechanisms on the interfaces. Some, for example, can do time synchronization, others maybe can't. Some can do time-aware transmission, some can't. And therefore, based on how that then fits with the application QS requirements and the mechanisms that are available on the end devices, the last step within the connection establishment and the stream registration process, all these mechanisms basically are integrated, and the network, we always name it late binding of the network, is then updated according to what is expected to be transmitted over the wire at the end. And this basically, at the end, this last step is always then network agnostic. So basically there, it's important to know which type of network is actually there. But everything up here for the application engineer is independent of which type of network it is. So here on the lower layer, we already need to know the concrete mechanisms. And in this case, it's Ethernet with TSN capabilities. But maybe, and that's going to be then part of the next talk. And this can also be 5G. And then this translation process just is a little different. But for the application engineer, this stays the same, and the networking below is exchanged. So, as a conclusion, I have presented you the different aspects that we cover within the UAFX networking. Mostly, this is content of part 82 with the connections to other parts, because at the end it's highly integrated into the process of the application engineering and the connection establishment. In general, if we talk about TSN in context of OPC UAFX, this is aligned to the 6802, and we basically try to be an early integration of that. And this upcoming C2C release is the base for these future plug-and produce TSN mechanisms. And for now, it's based only on priority requirements, but in future there will be more differentiated traffic types supported. In general, this networking and interoperability, and you have seen it already, I think yesterday in the C2C demo, was already presented on the Hannover Messe. Also, we have for the TSN parts and the quality of service that is specified in the part 82, but also for the Outlook, we have a TSN demo that was also already visible at the fair. And will be visible also later today in the session. So there we will basically show again hands-on how this priority-based and the plug-and produce TSN can work. So then thank you for participation, and I guess we first jump over to the next session and then handle the questions after on. Thank you very much.
I'm from Siemens, Germany, and I'm active in the OPC Foundation and covering the topics QS integration. So I'm more focused on the communication part of the OPC UA layered stack architecture. And if you look at this figure, we saw that before in a different slide from Peter. Here we are emphasizing the relations to QoS needs and requirements in the different areas where OPC is used. So we see, for example, in the cloud area, we need a reliable streaming of data and events. And in the shop floor for C2C, D2D communication, we expect cyclic process data exchange. And of course, we will need reliable, ultra-reliable, low-latency communication for wireless communication between robots, for instance, and that's something we like to work on with 5G ACA to specify the requirements for that. Here's one use case example where we see two collaborating robots, one mobile and one stationary on the right side, which need to collaborate. And for that, of course, we need a wireless connection. And in combination with safety, we have additional requirements, not only mobility, but also the requirement of a reliable and low latency communication. And why is that? So OPC safety is functional safety, and functional safety needs to make sure that any failure in your device will not lead to human or physical damage in your system. So we have a layer protecting your application and from that failures, and to make that work and to allow the safe interaction between these robots, this layer exchanges messages between the two robots. So the yellow part here shows the OPC UA safety part, which needs to send out cyclically time-critical safety messages, which are then received by the other side. There is a kind of watchdog which is looking at the incoming frames, and if some frames are missing, that signals the safety layer that there's something wrong. Maybe there's a failure on the other side, and the system then goes into the fail-safe mode, so in full stop. And of course, I do not want to have that because of bad communication relations, but only if there's a real error in the system. And that means for wireless communication, we really need a kind of guaranteed bandwidth and a reliable connection. And that's even more important than the bounded latency we also need, because bounded latency then guarantees us that these messages can be sent out quickly and exchanged quickly. And the more quickly you can send out this safety message, the more efficient and the more performant you can create your safety application, because then you can limit the safety space of your robots and make your and set up your system in a more cost-efficient way, and even make it work faster and smoother. The lower parts and the part where OPC UA gets connected to the or mapped to the underlying network infrastructure. And as said before, we modeled the QoS requirements as an integral part of OPC UA, so that an application engineer can tell easily what requirements he would need from its network infrastructure. You see that in this orange block. And with that information, it's easier to roll out that stream from one end to the other. And the reason why we did that is first of all, OPC UA will be located in various network areas. So, and maybe a customer decides to take its application one day and move it from a wired device to a wireless device. And it would be good if it would not need to change too much in his application configuration. So the QoS requirements would be actually the same at the end, whether it's put on a mobile robot or on a mobile HMI or somewhere in the industrial, behind the industrial LAN on a static stationary host. So that's the idea behind these QoS requirements. And with this information, the stream then can be rolled out, and we would like to achieve an easy way to interconnect all those participants over different network areas, as there are this wired network on the mobile robot or the 5G system, of course, and other parts in the network which may be involved for this stream. And for that, we need some building blocks inside our network areas. So for the wired part, for sure, we will use TSN streams to create a reliable transport stream. 5G provides several means. So a good starting point is just to use the QoS flows, the CDU session with layer 3, which already provides guarantees up and downlink bandwidth. And we have a certain, depending on the 5QI value you select, so the kind of traffic type you select for this PDU session, you will also get some reliable amount of reliable communication, and also some latency guarantees if you do not have really high-end demands on your system. But that would work fine out. And to interconnect all those different parts of the network, we see deterministic networking as one of the key technologies here to interconnect those parts of the network. And this allows you to have end-to-end QoS across routed IP networks. And I think that's quite reasonable to have that in a mobile situation where you for sure will cover big areas in your shop floor. And for that, we assume that routing will be an integral function in your industrial service infrastructure. Of course, we saw that before. 5G also provides a logical TSN bridge mechanism, so you can also use that if you do not need IP connectivity. You want to stick with layer 2 connectivity because of performance reasons, or to be compatible to field buses in the shop floor. then you can also use this technology. And putting all these building blocks together in one big picture, then we end up in the layered stack architecture. Peter showed us some similar figure before. Now I will concentrate on the mappings between the two layers. So above we see the OPC UA and OPC FLC blocks in blue and yellow. And below we have the network layer with the several technologies. From the bottom, we see layer 2 technologies like Ethernet, TSN, and Wi-Fi, and of course 5G. On top, or in the middle, we see the layer 3 connecting technologies providing certain types of QoS, differential services. We know that we use that since years in IP, in IT technology, and DetNet is something I mentioned before, which provides us guaranteed bandwidth and so on. And we see that OPC is capable to be mapped on more or less all of those technologies. We call that transport mapping. And with that, we have a flexible toolbox to allow our applications to run on different types of networks and to guarantee arbitrary connectivity. But one important aspect from our point of view, even if it's not a real OPC problem, but thinking about a shop floor situation or a factory situation where you have many different areas in your factory which are separated in different networks, where you have several people, each of them responsible for one part of the network. And if you want to make sure that data is flowing from one end to the other, here in that example, from the shop floor inside the machine to the industrial data center, maybe even on a network container, then we need some means to handle that easily, because not only connectivity is important between those end devices, we also need to make sure that the reserved bandwidth, the resources which are reserved on the way, that these are rolled out accordingly. And for that, a signaling protocol between those participants is of big importance to make sure that this works dynamically and QoS streams can be rolled out easily without twiddling all the management tools you might have in those several areas. Okay, and last slide. Yeah, and to sum it up, so we see that 5G ACIA is really ensuring that the interests of the industrial domain are driven as needed, especially in the 3GPP, so that we get the right standards and regulations for our use cases and needs. And the OPC framework provides enough flexibility to adopt and to integrate 5G communication to gain that mobile and reliable connectivity. Of course, we want to integrate together with the existing or upcoming standards like TSN, Wi-Fi, and DetNet. We see that Peter mentioned it, I think, before. 6802 is one of the key elements which helps us to gain interoperability for TSN devices and in a converged industrial network. And the as I said before, it's important for OT customers to get that system integrated and running as smooth as possible. And for that, we make sure from a technical point of view that we keep a clear layering between the different layers. And we need well-defined interfaces to do that transport protocol mapping. And the next steps for that in cooperation with 5G ACA will be that Julie mentioned before, we will have a deeper look on the use cases. We'll talk about architecture aspects, refine the discussion of QS mapping, and also talk about how to orchestrate applications on top of a 5G system. So thank you.
Thank you, Alexander. Thank you, Lukas, for sharing insights with us about OPC UA and UAFX over underlying networks such as Ethernet, Ethernet TSN, and 5G. We are now coming to two demonstrations. The first demonstration will be given by Lukas Wuesteney about UAFX over TSN. This demo we also presented a few weeks ago at Hannover Fair. And then next we have a demonstration by Josef Eichinger, Huawei, which is making use of the multi-vendor demo that we have introduced to you yesterday with the bottling line reference application. And Josef will explain to us how 5G has been integrated into this multi-vendor demo, and he will also talk about the key performance indicators, the KPIs related to the millimeter frequency band that was being used in this demonstration. All right, with that, I hand over to you, Lukas.
Welcome also from my side to the OPC UA/FX over TSN demo. This demo is about presenting what is currently available in the first version of the release and what will be the goal of the OPC UA/FX over TSN in the future. So let's start with our multi-vendor topology. As you can see on our setup and also in the topology on the monitor, we have 3 different switches in our network and we have 2 different end devices. Additionally, we have 2 Raspberry Pis which produce our video streams that you can see on our monitor. As a last device, we also have a PC that is available for the load generator that we will use later to show that the mechanism actually works. And the PC is also running our CUC and connection manager unit that is available for configuring our OPC UA applications. And we have our CNC on our PC running, which is configuring our network. So let's start with the scope of the first OPC UA/FX over TSN release. The scope of this release is that the end devices do not transmit synchronized to the network, but these end devices send the data with VLAN tags. The information about the VLAN tag is derived from a mapping table process. On this slide here, you can see how this process is working. The application engineer is setting the priority label and category inside the application. This is a very abstract information and is very simple to decide on. Then, automatically, this information is compared with a mapping table. The mapping table was provisioned by a network engineer and is then translating the priority label information into concrete either PCP values for VLAN tags or DSCP values for IP headers. These priority values are then used within the network to give certain guarantees to the traffic of the devices. The complete network is configured statically and also with the same mechanisms. All the devices are consistent in the configuration. In our setup, we have a class-based QBV schedule running where we can separate 2 different high priority classes and the best effort phase. You can also see this right next to our topology on the web interface of the TSN configuration. So let's start with our actual OPC UA over TSN first version demo. we have the two Raspberry Pis transmitting the video streams. One Raspberry Pi having a webcam, which is some sort of a control of our machine. And we have some best effort video stream that you can also see on the monitor. The information model defines that the priority label for the critical traffic is set to high, and therefore it has the PCP value 6 and will be secured in the network if we now enable our load generator. You can see that the best effort video is crashed, but the other video is still running perfectly. If we now switch the configuration of our surveillance video also to best effort by just changing the priority label to best effort, we can then see that we can crash also this video. This shows that now both videos are running in our best effort phase and therefore are not secured from any application consuming too much bandwidth. You have seen that it is very simple in this first release for an application engineer to already set a certain level of quality of service that its application will get within the network. Depending on the network configuration, this can be done with different mechanisms. We have decided for the class-based approach, but you could also use strict priority or frame preemption or a combination of any of these. So let's come to the outlook of this demo. The OPC UA-FX over TSN is based on what the OPC Foundation, the OPC UA TSN group, and also other profile groups are defining. In the OPC UA-FX over TSN in the future, the end devices will communicate their exact requirements on quality of service to the network. These requirements are then processed by the CNC and configured in the network. We have now here our BNR controller, which consumes the buttons and transmits them into the network, and the controller from Schneider on the left-hand side is then defining which LEDs should flash. So we can enable this application, and we can see that all the buttons flash synchronously. If we now press different buttons on the right-hand side, we can see that the application reacts to this. Also in this case, the application engineer has defined a priority label. In this case, it is not the priority label high as we have seen for our video stream, but it is the priority label critical, and therefore it will result in a different PCP value. Again, on this slide here, you can now see the process, how this is done in the future. We have again our priority label configured by the application engineer with additional quality of service requirements like timing informations and deadlines. We have our mapping table, and therefore we can determine all the values that need to be communicated via the CUC to our CNC. The CNC is the unit that is responsible for the network configuration. The CNC then rolls out a schedule within the network. This can be either like direct schedules for QBV, or it just knows about the different streams that are available and designs them in a way that there are no collisions. In our case, we have a class-based schedule in the network, and we have exact timing offsets for the end devices such that we have no collisions in the critical traffic. You can also see this on the right-hand side of our topology in the schedule. Additionally, you can see below the topology the two streams that are configured. On the one hand side, it is the buttons that are consumed by the Schneider device and the LED information that is consumed by the BNR and the other Schneider device. So if we now enable the load generator again, we can see that our best effort video is crashed, but everything else is running because we have configured the priority labels high and critical and therefore have exclusive guarantees to our applications. If we now stop the traffic and disable the application for a second, we can now set our application to best effort. This will result that with our mapping table, we will not receive the PCP value 7, but we will receive the PCP value of the best effort. And if we enable the application, it first looks like everything is running fine. But if we now enable the traffic again and reduce the available bandwidth, we can see that our LEDs are frozen. A few packets might go through, and therefore we might see sometimes a jump of our LEDs. But in general, the application does not work anymore. So we can now stop our traffic again and directly see that our application restarts and operates as normal. Also, the video stream is recovered. As you have seen, also in the future, it will be very simple for an application engineer to define the quality of service requirements that are needed by the application. And it is a very simple process that these are then processed by the network and that the whole network basically works to achieve these goals.
Thank you, Lukas, for this interesting demonstration about UAFX over TSN. It's always good to see things live and in practice, in reality. Even the theory and the concepts are certainly the basis for that. So thanks to you. We are now coming to the next demonstration, which is about OPC UA and UAFX over 5G. You see here a picture of a demo that we did a few weeks ago during a webinar we jointly did with the 5G ACIA. So you see the multi-vendor demo that we explained in detail on day one of our digital event, which is showcasing controller-to-controller connectivity over a common network infrastructure. So in the webinar we highlighted the integration of 5G. So you see here the two antennas on top, provided by Huawei, also member of our field level communications initiative steering committee. So what we did for this demo, we have been replacing wired connections with this 5G system using millimeter frequency band. And Josef Eichinger from Huawei, standing here on the right hand side, is explaining the details about how this integration was done, and he's talking also about the key performance indicators, the KPIs, using that display with a user interface you see here as part of the demo wall. Okay, with that, let's hand over to Josef for his explanations.
Yeah, what we have here is, as I said, a fully integrated 5G network. What is here all in the box, all of the necessary components are integrated here in this rack. Before I go into some more details, I just want to spend a couple of minutes to talk about different frequency band what we have in the 5G, mainly targeting also industrial use cases. Everybody knows this not magic, but the well-known and famous C band that is somehow in this 3.4 to 3.8 gigahertz band, at least in many countries. And this is the primary band for the current usage of 5G in industrial environments. And all of the control-to-control use case, what we have here on the demo wall, could also run with the C-band, with this existing commercial solutions, what you can buy right now from the vendors. The C-band has one limitation, and that is available bandwidth of 100 megahertz only. And what we want to demonstrate here is with the prototype, what we have built, that we can also use the millimeter wave frequency band that offers a much higher bandwidth, up to 800 megahertz at the end. And what we now did is here, we have connected the baseband unit to, on one side, to the industrial controller. For instance, here's a Bosch Rexroad controller, and you see everything is here is green. That means the connection is error-free. And on the other side, on the RF side, we have connected it to the RF antennas, what you see here on the top of the demo wall. These are millimeter wave antennas capable to cover a quite big area in your factory. It could be a 10 by 50 meter area or even larger with enough capacity and radio. And for some reasons, maybe you need more if you want to extend your use case scenarios and if you want to go more ahead with deployment of 5G in your factory environment. As this is what we have here. It's live running. It's already, you could hear it if you are here on site because all of the machineries, they have some noise, at least from the computing point of view. This is what we have here in the setup. Now let's talk a bit more about the KPIs and the technical insights. And for this, we have prepared on the demo wall a kind of screen, a GUI. And this is part of the demo wall. You can see it. It's part of the network here. And it demonstrates what we are currently doing in the network. We have a system that operates in 26 gigahertz. That means it's a millimeter wave range with a 200 megahertz bandwidth. For sure, it could go up to 800, but for this, we only need this 200. We see here in this display that we have a latency that is quite low. For the control-to-control application, it's not necessary to talk about 1 millisecond. It could be also maybe 5 milliseconds or 3 milliseconds. That's fully enough for these applications. But actually, we want to demonstrate the ultra-low latency and reliable communication because this is a key for the integration of 5G with OPC UA, as Peter and others have already shown today in the slides. And this is mainly what we have set up here, and the demonstration is working fine. It was also working so many days in the Hannover Fair without any issues. That means we are quite happy with this integrated demo with OPC UA and our 5G system. And thanks to the OPC Foundation, to Peter, that we could make it happen and that we could really integrate this. And I'm looking forward to do more if we go from control to device aspects and with all of the new things what we want to develop together.
Yeah, thank you for your support, Josef.
Thank you, Lukas. Thank you, Josef, for explaining to us the two demonstrators. For those of you that are interested to learn more about the combination of OPC UA with 5G, I have included here links to a recording which is available over the 5G SIA website and YouTube channel. This is about a joint web seminar that we did recently. It was actually on June 22nd. And in addition to the various presentations by different experts, we have also a full recording of that live demonstration, including the part that we just showed with Josef from Huawei. Now with that, I think it's now time for getting started with the Q&A.